Good morning and good afternoon. Thank you for attending the CXL Consortium CXL 3.0 Enabling Composable Systems with Expanded Fabric Capabilities webinar. We will have a Q&A session at the end of the presentation, so please submit your questions via the chat feature and they will be addressed. At this time, I will turn the presentation over to Danny Moore from member company Rampus.
Hey, thanks, Elza. Hello, everybody, and welcome to our 3.0 webinar. We're all really excited to introduce the latest 3.0 specification and some of the novel device types, capabilities, and interconnects that the consortium has been busy architecting. My name is Danny Moore. I'm a senior manager in strategy and product management at Rambus, where I primarily drive product planning and in our data center business unit, kind of with a focus on CXL. I've also been fortunate enough to have been involved in the consortium since its beginnings in 2019, and currently I'm an active contributing member in the CXL marketing work group, and most recently been focused on the 3.0 specification release. My co-presenter is Debendra Sharma. He's one of the foundational architects of the CXL specification. He resides as co-chair of the CXL Technical Task Force and is a senior fellow at Intel. So in the CXL Consortium, we're always interested in growing our participation. There's a few different levels that you or your company can get involved in CXL. There's an adopter membership, which is free of charge. Or if you choose to take an active role in the specification development, you can sign up for contributor or promoter levels of membership. You can head over to computeexpresslink.org for more information. Our membership continues to grow year over year. We're currently over 200 plus member companies. And like the 200 plus member companies, our board of directors represents a wide array of companies from industry, including CSPs, hyperscalers, the major CPU and accelerator vendors, memory suppliers, and server OEMs. To reiterate, and as I mentioned, we're always interested in strengthening our member community. So if you're currently not participating, please do head over to computeexpresslink.org and find out how you or your company can contribute. So as I mentioned previously, it was back in March of 2019 when the 1.0 specification was first released. And by September, we'd already published the 1.1 specification and officially incorporated the CXL Consortium. By November of 2020, we had released the 2.0 specification. And just in August of this year, we published the 3.0 specification. I won't get into any details regarding features and capabilities that come along with that specification cadence, as Debendra will be walking you through some of those historical details before jumping into the 3.0 features and capabilities. So with that said, I'll hand it off to Debendra to provide a technical overview of the CXL specification. Thank you very much.
Thank you, Danny. Hey, greetings, everybody. Here's the agenda for today. We'll start with a recap of the industry landscape and CXL, as well as a recap of CXL 1.0 and 2.0. Then we're going to dive into the CXL 3.0 features as well as capabilities and conclude. There have been a lot of webinars where we have talked about CXL 1.0 and CXL 2.0 in a lot of detail. So you may want to go look into those to get more details. Today, I'll just do a very brief recap of those. So when we look at the industry landscape today, we see some very clear megatrends emerge. Cloud computing has become ubiquitous. Networking and edge computing is exploding, increasingly using the cloud infrastructure, artificial intelligence and analytics to process the huge amount of data that we are generating. All of these are driving a lot of innovations across the board. We see the increasing demand for heterogeneous processing as people want to deploy different types of compute for different applications, whether it is general purpose CPUs, GPGPUs, custom ASIC, FPGA. Each of them is important and best suited to solve some class of problems. Now, in addition to the demand for heterogeneous computing, we also see the need for increased memory capacity and bandwidth in our platforms. And that's natural because as we process more, you need to feed the beast, so to speak. We also are having a class of memory between DRAM and SSD that needs to be thought of as a separate memory tier, offering compelling value proposition due to its capacity and persistent semantics. So these mega trends that we are discussing here, they take advantage of these types of memory in addition to the evolution in the traditional DRAM memory and storage. Compute Express Link is defined ground up to address the challenges in this evolving landscape by making both heterogeneous computing as well as different types of memory efficient. And it's meant to sustain the needs or the demands of the computing segment for many years to come. So brief, CXL, we're going to look into these in a lot of detail. It's built on PCI infrastructure, adds memory and coherency semantics, and it is an open industry standard, as we had talked about. So CXL has followed a three-pronged approach for ensuring the ease of ecosystem adoption. At the fundamental level, CXL is built on top of PCI Express infrastructure and leverages PCI Express. It overlays the caching and memory protocols on top of existing PCI Express protocol. It runs on PCI Phi, runs on PCI channels. There are three protocols: CXL.io, which, as we said, is identical to PCI Express. It is used for device discovery, event reporting like errors, etc., I/O virtualization services, direct memory access for data move. Pretty much we didn't want to reinvent any of that wheel. What we did was we added the CXL.cache semantics for doing cache coherency and CXL.mem for doing the memory protocol, right? Those were the key addition that we did in order to enable the types of usages that we talked about. Now we start with the 32 gig data rate because of the high performance it offers. PCI adoption helps lower the barrier of entry since PCI Express Phi is ubiquitous. It has got low latency characteristics and low power characteristics. And this also enables us to do plug and play. A customer can choose to use a PCI slot to plug in either a PCI device or a CXL device, depending on the need. And different customers will have different needs. The second aspect of CXL, so the first aspect was plug and play with the CXL PCI infrastructure and just build the coherency and memory semantics on top of that. The second aspect is the low latency aspect. It is critical because caching and memory protocols need low latency to not adversely affect system performance. We are expecting latencies in the range of existing symmetric cache coherency links for the cache and memory traffic. For example, the specification provides guidance on expected latency, 50 nanoseconds pin to pin for snoops, 80 nanoseconds for DRAM accesses pin to pin. Now, there is also a reporting mechanism so that system performance is not adversely affected if slower memory devices are used. You can report that, and the system software will map things accordingly. Third, and another important aspect is Compute Express Link, CXL. It's an asymmetric protocol. So the protocol flows and message classes are different between the host processor and the devices. And that's a conscious decision to keep the protocol simple and the implementation easy. That's the reason why you will see the home agent is present in the host processor, and that tends to be very dependent on the inherent microarchitecture, keeps changing. Different people do very differently. We have abstracted all of those away and given some very simple, messy protocol-based coherency semantics, and even for the memory side, you don't really need to understand how cache coherency works. You just need to provide the data along with the metadata. CXL 1.0 and 1.1, it's a direct connect between a host processor and a device, and it targeted three types of usage models. The left is a type 1 device, which basically needs caching semantics for usages like a smart NIC to deliver better performance. Examples would be like if you do PGAS ordering model, where that ordering model is different than the PCI Express ordering model. Now, if you do the caching, you can, of course, complete those things within your local cache, right? And you can enforce that ordering or enhance atomics operations. So this can be done in addition to the traditional PCI style load store IO. So that's for the type 1 device. The middle example is a type 2 CXL device. Typical usages include things like GPGPU, FPGAs, dense computing. These devices have some local memory attached to them, which are used for their computation. We expect them to implement all three protocols, CXL.io, CXL.cache, and CXL.mem. Caching and memory semantics would be used to populate and pass operands and results back and forth between the different computing entities with very low latency and high bandwidth efficiency. System on the right is a type 3 device. And the usage here would be things like memory bandwidth expansion, the memory challenges that we talked about, memory capacity expansion, and also tiered memory, including storage class memory. So these only need to implement the CXL.io and CXL.mem semantics. The memory will be mapped to the system memory as cacheable memory. The host processor orchestrates the cache coherency here, and that relieves the devices from having to implement the complex coherency flows because of the asymmetric nature of CXL. So the device doesn't even need to know anything about caching semantics. It doesn't need to implement CXL.cache. So after CXL 1.0, we did CXL 2.0, where 1.0, 1.1, we did CXL 2.0, where we added support for pooling of resources across multiple servers, as shown in the picture here. Now, these resources can be accelerators or they can be memory. Memory pooling is done at a finer grain level and can be supported by multiple logical devices, which can support up to 16 hosts or 16 servers or virtual hierarchies. We use the terms interchangeably. And they are all assigned non-overlapping memory. So for example, if you look at the picture, D3 is assigned between two sets of servers or two sets of hosts, H3, which is color purple, and H2, which is color green. So you can do up to 16. And these resources, by the way, can move between different hosts following a standard hot plug flow. Now, this capability with CXL 2.0, it enables resources like accelerators or memory to be pooled at the rack level. It's a huge innovative breakthrough, as we no longer need to have captive resources in a tightly coupled cache coherent system. Today's systems, you got memory, you got IO, you got GPUs, you got whatever, right? You got your accelerators along with your processors. Those are tightly coupled to that particular server. Or let's say there is another server that needs more memory. You cannot borrow memory from a neighboring server and still use the load store semantics. With the CXL 2.0, we just enabled that. It's a huge breakthrough from that perspective. And now what we can do is that we can dynamically compose systems with additional memory or accelerators from the pool. And in the picture, even though it's only memory pooling, you can imagine you have accelerators in the picture and it can be pooled similarly, right? So for example, if a host needs an additional 3 accelerators for a task that it is running, it can come to the pool, get the 3 accelerators. Once it is done, it can release them back to the pool and somebody else can use it. So that results in significant total cost of ownership benefit, along with delivering better power efficient performance. CXL 2.2, of course, enables a single level of switching for the fan out. I mean, fan out is where you can have a single link and then you can connect multiple devices underneath a switch. So that part we enabled with CXL 2.0. And of course, the more advanced thing is the pooling notion that we talked about. So fundamentally, if we look into CXL 2.0, we talked about resource pooling and disaggregation, and that happens through the managed hot plug flows to move resources across different hosts. A type 1 or type 2 device is assigned to one host at a time, behind the switch. It's assigned to one host at a time. Now a type 3 device, if it is a multi-level MLD kind of device, multi-logical device, it can be assigned to up to 16 hosts at a time, and you can still move them, and you can move different chunks of memory across the hosts, and it enables pooling at the rack level. And all of these have direct load store, low latency access, similar to memory that is attached to a neighboring CPU socket. Very different than doing an RDMA over a network, which has got much, much higher latencies. We defined persistence flows to support persistent memory. We also have defined how a fabric manager needs to work with the APIs for the switches as well as for the devices so that you can manage this resource migration across different hosts. We enhance security by adding authentication and encryption with CXL 2.0. Fundamentally, CXL 2.0 goes from a node level to rack level connectivity. It enables the disaggregation of the system with CXL, which basically is done to optimize resource utilization. And that in turn will lower total cost of ownership and give us better power efficient performance. All of this while CXL 2.0 being fully backward compatible with CXL 1.0 and CXL 1.1. Now, let us recap the industry trend that we just talked about, right? So from the trends point of view, we got use cases that need ever higher bandwidth. And, that's because we got a lot of high performance accelerators. We need system memory that, memory bandwidth, the demand is insatiable. You've got smart NIC, you've got leading edge networking, all of these things, right? As you are processing more, of course, you need to have more bandwidth that needs to move around in the system while maintaining low latency characteristics and low power and all of those good stuff. Now, we also know that CPU efficiency is declining due to the reduced memory capacity and bandwidth per core. So we need to shore that up with CXL. We need to also do efficient peer-to-peer resource sharing. And going to see this in some of the examples across multiple domains. And we have memory bottlenecks due to the CPU pin and thermal constraint because the DDR buses are pin inefficient. So those are the things that are in the industry trends. Some of them we have solved with CXL 1.0 and 1.1, 2.0. With CXL 3.0, what we have done is we are introducing things like fabric capabilities, and we're going to see more of that. Things like multi-headed devices, we got enhanced fabric management, we got composable disaggregated infrastructure that we're going to see examples of. We have better capacity and better scalability, better resource utilization for memory pooling, larger systems, new enhanced coherency capabilities, and improved software capabilities. At the same time, we have managed to double the bandwidth while keeping the latency flat. All of this while we are being fully backward compatible with CXL 2.0, CXL 1.1, and CXL 1.0. From a CXL 3.0 specification point of view, this is again, what are the capabilities? Of course, we got better bandwidth, we got fabric capabilities, we got improved memory pooling and sharing capabilities, enhanced coherency semantics, peer-to-peer, all of those things, and we're going to go through those in a lot more detail in the upcoming slides. This is a nice tabular view of the different features that are available with the different revision of the specification. We started, as I said, with 32 giga transfers per second in CXL 1.0. We kept that through 2.0. With CXL 3.0, we are doubling the bandwidth to 64 gig. Of course, you're still going to be operating at 32 gig, but maximum data rate is 64 gig. The split were 68 bytes up to 32 gig. Of course, that will be maintained all the way through 3.0. But with 3.0 at 64 gig, we run it at 256 byte flit. Type 1, Type 2, Type 3 devices have been supported from 1.0 days, so that continues. But with 2.0, we saw the memory pooling, also accelerator pooling with MLDs, starting with 2.0, continues through 3.0. We define the persistence flows with 2.0 onwards. IDE is the security enhancement that I talked about. So that's there from 2.0 onwards. And single level switching got introduced in 2.0. Multi-level switching got introduced in 3.0. Now, in addition to that, CXL 3.0 has got other features like direct memory access for peer-to-peer, which results in better bandwidth and of course results in a lot better bisection bandwidth in the system. We got enhanced coherency to better manage accesses, which will result in better efficiency in the system, as we will see. We also have defined memory sharing across multiple nodes. This is a very new concept, not just pooling, but sharing of memories, which enables us to go for a lot of different usages. We also are enhancing the number of type 1, type 2 devices that can be supported per root port. So this goes from 1 to multiple, and of course fabric capabilities. And we're going to go through this again in some detail in the upcoming slides. So first thing is that we did double the bandwidth with CXL 3.0. So we basically use PCI 6.0 PHY running at 64 giga transfers per second. In order to go to 64 giga transfers per second, we have to do PAM4 signaling, which results in very high bit error rate. And this has been mitigated by PCI 6.0 with the use of forward error correction, or FEC, and 8-byte CRC. The PCI 6.0 FLIT layout is shown on the top picture there. So you got some number of TLPs, which stands for transaction layer packets. And then you got DLP, which is data link layer packets. And then that's followed by 8-byte CRC and then a 6-byte FEC. And the FEC, basically the way it works is that you get a particular FLIT, you correct that FLIT using the FEC, then you apply the CRC. If the FLIT passes, you consume it. If it fails, you basically cause a link level replay. There is a PCI webinar on that goes through these in a lot of detail. And also there are a few papers. One of them I have listed here. If you are interested, you can go and take a look at that paper. It goes through a lot of the technical details behind those. Now, for CXL 3.0, we took advantage of the same thing. There are two types of FLIT arrangement. The picture on the middle shows what we call a standard FLIT layout. As you will see, it's very similar to PCI 6.0 FLIT layout. We got a 2-byte FLIT header. Basically, you need the header in the beginning to tell which stack it is going, whether it is an IO FLIT, caching, CXL.cache FLIT, and CXL.mem FLIT. In addition to that, you're going to get all the things like sequence number, things that you need for the management of that particular FLIT, right? Sequence number, ACK, NAC, replay, those kind of things. Now, the 8-byte CRC, you will see, is in the same place. And then you got the 6-byte FEC. And within the rest of it, you got what we call the data, which can be either CXL.io or CXL.cache or CXL.mem. We also have a latency optimized version, which is the picture at the bottom. Basically, the 256 bytes get split into 228 bytes. Each of them is independently protected by a 6-byte CRC. And the notion here is, but the FEC is across the whole 256 bytes. So the idea here is that when you get 128 bytes, if you pass the CRC, you just consume it without even doing an FEC. If you fail the CRC, then you gather the entire 256 byte, apply the FEC, then do the independent CRC check on each 128 byte half. If it passes, you consume. If it fails, you go and ask for a replay. And that results in much lower latency because you are only doing the FEC correction when there is a failure. And also the CRC, the accumulation is not the 256 byte, it is at 128 bytes. So that's the reason why we result in zero latency adder and all of that good stuff. And these things extends to the lower data rates also, because once you're in a particular type of FLIT mode, you need to stay in that particular FLIT mode. You cannot go back and forth between them. So we also have enabled, because the FLIT sizes are bigger, we have enabled several new CXL3 protocol enhancement with this 256 byte FLIT format. Now coming to some of the protocol enhancements, right? There are two major ones that are very simple constructs but extremely powerful and very profound. They're going to have big, profound impact in the land of compute for decades to come. Those are unordered I/O, UIO for short, back invalidate, BI for short. And basically, what happens is that there are multiple reasons why we went with this. One of the reasons is listed here. We basically wanted to enable non-tree topologies, which is, so far, if you look into PCI Express or CXL, those are based on tree topologies. And we need a tree topology because on the IO side, you have what is known as producer consumer ordering semantics, and those semantics gets enforced at every entity, whether it is a switch, whether it is an endpoint, whether it is a root port. Everybody enforces that producer consumer semantics, and that doesn't work if you do anything other than a non-tree topology, hierarchical tree topology. And that works fine. That works for a lot of applications, but for a lot of these, like fabric kind of application where you want to have resources that are disaggregated, you want them to talk to each other directly. You don't want to always go through the host for every communication, right? That basically causes the host to be the bottleneck. So in this example, let's say I got a device D1, and that wants to access HDM memory, which is residing maybe in D5 or D6, but HDM stands for host managed device memory. It's basically coherent memory. So it wants to access that. Now, in today's mechanism, with CXL 1.0 or 2.0, it would have to go through the host, which owns the cache coherency for that particular memory. And then it is going to go through the access. The host is going to fetch the line from the particular device, let's say D5. If it is a read, it's going to then send it back. Instead, we want to just bypass the whole thing and go to the device directly. So that enables, first of all, a lot of unnecessary traffic, and also it enables parallel paths, which is good from delivering better bandwidth, better latency, and all of those. So those are the things that enables with the peer-to-peer. Now, what happens is that now, why do I need the unordered I/O and the back invalidate, right? Now, let's say if you're trying to read something, D1 tries to read from D5. It's coherent memory. Now, if it is coherent memory and let's say D5 notices that the host has that particular line as exclusive, right? If it has it exclusive, then it may not get the latest and the greatest copy of the data. Today, with CXL 1.0 or 2.0, there is no way for a device to really send a snoop back to it's an asymmetric protocol. So what we did was that we basically took the CXL.mem, which has got the least dependency from a protocol dependency point of view, and send the back invalidate back to the host saying, hey, somebody wants to access this particular line, and the host will then, its cache coherency mechanism will kick in, and it's going to then respond to that back invalidate. So most of the time, you really do not expect there to be a conflict, so that you're going to just go to the device, figure out nobody has it, so you can complete your transaction. In the rare case where that is not the case, you're going to invoke the back invalidate flow. With the UIO, what happens is that once you're trying to mix the coherency world with the producer consumer world, it runs into problem because you got multiple paths, right? So unordered IO is a way to break that. What unordered IO does is it moves the producer consumer enforcement to the source. So this is these two mechanisms are going to have that profound impact. Now, with that, what happens is that even for IO traffic, I don't have to have a tree hierarchy, because guess what? My ordering point is at the source. D1 has to enforce that ordering. Writes are no longer posted. Writes will get a completion back. So I know when a write made it, so then I can basically do my producer consumer ordering that way. So these are the two constructs which have got extremely powerful, and you can build pretty powerful systems using disaggregation and by composable system using fabric topology with these two protocol enhancements. So Fundamentally peer-to-peer with this doesn't to coherent memory doesn't need to involve the host unless there is a coherency conflict. So that it removes that bottleneck. So for example, if you are a NIC, you can directly access the HDM memory, which may have its own local processing, and simply inform the host only when there is a coherency conflict. Otherwise, you can just complete it at the device level, at the type 3 or type 2 device level. With CXL 2.0 and 1.1 and 1.0 before that, we had a bias flip flow. And of course, I talked about why we need back invalidate from the peer-to-peer access. Now, there are other reasons why we also needed that. We do have the existing bias flip mechanism, which is available for type 1 and type 2. It's not for type 3. And the problem with that is that needs to be tracked fully since the device could not back snoop the host. So you need to basically have a complete, whatever memory you are hosting, you need to track the entire thing either through the directory or whatever is the size of your snoop filter dictates the size of the memory that you are mapping into the HDM space. Now with back invalidate with CXL 3.0, we can enable snoop filter implementation, resulting in large memory that can be mapped to HDM. Now let's look at the example here. The system on the left shows the type 2 device with a snoop filter implementation. It uses that to track which lines are with the host. If you look at the picture on the right, now when we get a memory read request to cache line X at the device level, let's say the snoop filter is full. So there is no, we are going to hold off on X. Now we are going to figure out where would X go. X would go into the same location where cache line Y is. So it is going to issue a back invalidate to cache line Y. And basically it needs to evict Y from its snoop filter in order to make an entry for X. So it goes that back invalidate goes in the CXL.mem channel, as you see, back invalidate Y. That results in all the snoop flows from the host side, host home agent side into other peer caches. It's all going to get resolved. Finally, you may end up with getting a memory write in this example to Y, and if you do the completion for that, the memory write goes to the device memory. At that point, what happens is that now you can make room for X, get the data for X, and then provide that data back to the device. So this basically enables to implement a snoop filter and still map your entire memory into the system coherency space or the HDM space. This picture here shows CXL 3.0. What happens is, earlier it was only a single level of switch. The picture on the right shows a hierarchical kind of switch. You can have one switch. Underneath that, you can have a set of switches, and you can have a lot of devices that can connect to a host. So we enable much larger fan out, much larger system construction with CXL 3.0 with multi-level of switching. The picture on the left shows more of a cascaded kind of switching mechanism where you got different devices connected, and they are like it's like a fabric kind of a topology where you got switches connecting to each other, and then you got multiple hosts, multiple devices connected, and you can build your system that particular way. The picture here shows multiple devices per root port, which got introduced with CXL 3.0. The picture on the left is the CXL 2.0 picture. Now notice that there is only one type 1 or type 2 device underneath a switch. You can have more memory, but you cannot have more than one type 1, type 2 devices because every link only tracked one outstanding caching agent, right, on the other side. With CXL 3.0, we have removed that restriction, and we can have up to, I believe, 16 of them that you can track type 1 and type 2 devices. Of course, you can have type 3 as many as you want, but multiple type 1, type 2 devices underneath the CXL 3.0 switch. So that gets enabled with CXL 3.0. Now, for CXL 3.0 also enables the notion of course, we had the notion of pooling with 2.0. We also enable the notion of sharing. We, of course, expanded the use case for the notion with pooling because we have multiple levels of switches, but What does sharing really mean, right? I mean, what sharing means is that if pooling effectively refers to you pick any given memory location, it is assigned to a given host at a given point of time. Now, at a different point of time, that same memory location can be assigned to a different host. As you go through the hot plug flow, but with sharing, what happens is that you can have multiple hosts share the same memory location in a coherent fashion. So how is that possible? Because each of the hosts are different cache coherency entities, right? I mean, they are independent systems. They just, there is no cache coherency. The home agent in H1, for example, is not going to talk to the home agent in H2 to orchestrate cache coherency. Again, these are very independent systems. They have got their own independent system map and all of those things, right? So what happens is that if you're a device, let's say, if you look at the picture device D4, you have the shared memory in D4. Now, what D4 will do is that, let's say, if it is sharing the memory across multiple hosts, and let's say 5 hosts want it shared, fine, you can give them shared, right? That's allowed. Now, if somebody wants exclusive, what happens is that you will you are going to launch the back invalidate flow for the other 5, wait for them to complete before you can give it to somebody who is asking it for an exclusive ownership. So that's the back invalidate flow that we introduced. And again, because it is there in CXL.mem, now you can only have type 3 device that really don't understand much about the cache coherency. They can just do the back invalidate to the respective to the hosts that are involved and enforce a shared coherent memory space. We have defined something called a global fabric attached memory GFAM, which can provide accesses for up to 4095 entities. So from 16 pooling in CXL 2.0 to 4095 that can not just do pooling but also do memory sharing. And of course, we have enhanced the CXL Fabric Manager to do all the setup, deployment, and all of those stuff. Actually, going back to that, let me elaborate a little bit on the type 3 devices. We have 3 basic types of type 3 devices that we have defined in CXL. We have the single logical device, SLD, which is assigned only to a single host CPU. Right? This comes from the CXL 1.0, 1.1 base. And I get this question a lot, so I thought I'll elaborate a little bit here. The other type is the multi-logical device, MLD, which we introduced in CXL 2.0. There, what happens is that you can assign the device to multiple hosts up to 16 for pooling. And the maximum number of hosts that can be supported at a time is 16. Then the third type, and you can also support multiple with 3.0, you can do, with MLDs, you can also do share. Now, with 3.0, we also introduced the notion of global fabric attached memory GFAM. This is the same as MLD in its basic capabilities, but support large scale in terms of the number of hosts up to 4095 that are actively using the device. And this scaling 4000 up to 4095 relies on the device directly participating in something that we call port-based routing, PBR protocol extension, and that comes with 3.0. So type 3 devices have got these 3 different flavors, SLD, MLD, and GFAM. And all 3 can be used within a switch hierarchy at any level. Now you can build a CXL switch with traditional hierarchical decode routing, HBR, as originally defined in CXL 2.0, or with the new port-based routing, PBR extensions that we have defined on 3.0. So the GFAM devices, they rely on PBR extensions to be supported by the switch, whereas the SLD and MLD can be connected to either switch type. Hope that clarifies that. Now, looking into multiple levels of switching, with the CXL 3.0, with 2.0, we only had a single level of switching and only one type 1 device. With 3.0, we have up to 16 CXL CAS devices. So 16 type 1 or type 2 devices. And of course, you can have any number of those type 3 devices that the fan out is going to support. Now, we talked about shared memory mechanism a few slides back. So this is just going through that in some more detail. Device memory can be shared across all hosts, and this is done. The usage model is to increase data flow efficiency and also improve memory utilization. So earlier there was no coherent memory mechanism for independent hosts, including the devices within the host, to do memory based message passing between them or semaphores between them. With shared memory, now those are possible. So now you can imagine building large HPC systems where, of course, you're going to have your pooled memory, but you can also have some shared memory where different entities are doing different compute, and they can just use the shared memory as a region where they can either pass messages between each other or do have common data structure there that they're all working off of. So we enable a lot of those usages with very large scale systems, right, up to 4095 under a switch hierarchy that we have. Now, this is the essence of the capabilities that we have. This slide talks to that, brought to bear with CXL 3.0. Now, just to recap, we have broken the limitations of tree hierarchy topology, which is enabling high bisection bandwidth with parallel paths, as you can see in the picture here. This is a true composable system, true fabric. There is nothing like a tree topology here. And of course, this is not the only way you can construct, but you can imagine constructing systems with spine level switches, leaf level switches, and the picture on the right shows basically a rack that's there. So you can do things, and at the bottom of it, you have got multiple hosts, CPUs, but fundamentally CPU is like a independent server, right? That's what it represents. It has its own memory, IO, all of those. You got some amount of memory, you got a bunch of accelerator, you got GFAM memory device, you got NICs, right? These are all the end devices connected through leaf switches, through spine switches. And the extension can be with 64 gigabit transfers per second per lane, and with cable, you definitely rack is within reach. And depending on the distance and how many retimers you use, or whether you go optical, you can do even a pod level connectivity, right? CXL3 enables for that. We also have enabled computational storage with CXL 3.0. You can have the memory, for example, that you see, you can have it do some local computation because it participates indirectly in the cache coherency by doing backend validate. So you can ask the memory entity to do some local processing, and it will still be coherent with the rest of the system. We do enable direct peer-to-peer, which will enable better performance. And of course, we talked about doing shared coherent memory that enables communication across hosts and devices using the load store semantics. So fundamentally, what you have is a set of compute nodes, a set of memory nodes, a set of accelerator nodes, and all of those, and the other types of IO nodes, and you can create fungible systems. And not only can you create fungible systems, like you can mix a compute nodes memory capacity grow by going to the pooled memory location, or going to the, it's going and asking for some additional accelerator. But also now you can have these systems work collaboratively through things like GFAM or message passing using CXL.io, all of those things. So we have all of these capabilities built in. It's fundamentally a tremendous breakthrough that we have been able to do with 3.0, right? We started with 2.0, and with 3.0, effectively load store interconnect is moving from the node level, which was, a single domain, a single server, to now to the rack level and beyond. So in conclusion, CXL 3.0 offers full fabric capabilities along with fabric management. We have expanded the switching topologies. We have offered enhanced coherency capabilities. We are able to do peer-to-peer resource sharing. We have doubled the bandwidth while keeping the latency flat compared to CXL 2.0, which is very important for us because we are doing coherency and memory semantics. And all of this while being fully backward compatible with CXL 2, 1 prior generations. And this backward compatibility is enables us to really innovate without having to create a lot of angst amongst people, right? Because their investments are protected, they can make the transition whenever they want to. It's going to just work. Of course, we enabled a lot of new usage models with memory sharing between hosts and peer devices. We, of course, support multi-header devices now because of the fabric capability. In other words, you can have a type 3 device where you can have multiple links talking to different CPUs directly or different switches directly. You got the enhanced capability, coherency capabilities with the backend validate. And we got the expanded support for type 1, type 2 devices. And with GFAM, we provide expansion capabilities for the current and future memory. So you can download the 3.0 specification. It's available. As Danny said, if you have not joined the consortium, please do join. The CXL journey, in my mind, it has just started. We have plenty of new innovative usages that we are working on to evolve this technology further in a fully backward compatible manner. And CXL is already changing the compute landscape, and it's going to change the compute landscape, continue to change the compute landscape very, very profoundly in the coming decades. So with that, we'll go for Q&A.
Yeah, thank you, Devendra and Danny. So we will now begin the Q&A portion of the webinar. So please share your questions in the question box. So the first question about the host cache that a GFAM device accesses for back and validate flow. Does it consist of a cache memory lines of other GFAM devices too? Or do they all have separate host cache for different GFAM devices? How about different media partitions in a GFAM device? Do they have a separate cache for each media partition?
So okay. I'm assuming the question is from the host perspective. If you are accessing a given, any caching agent, right? If it is accessing a memory location, it is doing that on a per cache line basis. So yes, the accesses will still be on a per cache line basis. As far as the GFAM device is concerned, it's going to, just like any memory device is concerned, it's going to provide that access. And if it is supporting the shared coherency across different hosts, it needs to then, of course, enforce that using hardware cache coherency mechanism. It needs to enforce that using the hardware cache coherency mechanism. Danny, did you want to add anything to that?
No, I think that covers it well.
Okay, thank you. With change in flit size, will CXL 3.0 remain compatible to CXL 2.0 devices? Can hosts or switches support mix of CXL 2.0 and 3.0 devices connected to the same switch or fabric?
So if you notice in the table that we showed, CXL 3.0 needs to support the 68-byte flit size as well as the 256-byte flit size. So yes, that's how it will interoperate, right? So 68-byte flit size at 32 gig is the lowest common denominator. So yes, switches and hosts can do the mix and match of CXL2 and CXL3 and it will just work fine.
Yeah, maybe I'll just add a small tidbit there. One of the primary goals in the CXL specification is to maintain that backward compatibility. So, we've taken cautious steps to make sure that compatibility is maintained as we proceed through the newer versions of the specification.
Okay. So the back and validate flow expects devices or switch to keep track the status of all cache lines. Otherwise, it will trigger BI on all peer accesses. Keeping track of all these cache lines will make switching devices more complex and will break the premise of keeping devices simple. Is that a correct assumption?
Okay, so let me answer the question first, and then assumption part we'll get to that later. These are all optional capabilities. Anytime you want to have a new feature, there is an extra amount of hardware that you need to build. That's expected. Now the question is that a hard does that cause a lot of complexity, right? Let's look into this. If you're, for example, doing type 3 memory, right, and that's pretty much what where you would expect, or even if a type 2, anytime you have a memory that you have mapped into the HDL space, fundamentally you are supporting the the meta bits, which are basically the directory. So okay, so those exist. Now, what you're doing is really looking into that and trying to figure out, do I need to issue a back invalidate? I don't think that's a huge lift. You're not participating in any other cache coherency action. All the orchestration still gets done by the host processor. So yes, I believe it is still really simple. And if I may, yeah, that assumption is not a correct assumption. It is still simple.
Could you repeat the latency limits you mentioned?
The latency is a guidance in the specification. What guidance we have given is snoop to response, pin to pin is 50 nanoseconds. And, if you're accessing memory like DRAM or HBM on a device side, it should be pin to pin 80 nanoseconds. It's a guidance. It's not a limitation or mandate.
Could you please explain the relation between UIO and BI again?
Sure. UIO, what it does is it basically moves the producer consumer ordering enforcement to the source. By that, what I mean is, let's say if I'm a NIC device, I'm doing a bunch of writes and reads to memory. Today, what happens is that I just issue those writes and reads, and I expect myself to follow the producer consumer ordering, and I expect the switches to do that and all of that. So as a result, writes I can just post, right? I can just send the writes and forget about it. With unordered IO, which is again an optional feature, what you can do is you can say, hey, look, I'm going to wait for, for the writes are not posted. I'm going to wait for the writes to get a response. And because I'm waiting for the writes to get a response, everybody else in the hierarchy, me as the source, meaning me as the NIC that is generating this, I'm going to make sure that producer consumer is enforced. Rest of you can do things and do these reads and writes in any order in the UIO. Why is that important and how does that work with BI, back invalidate? That's the question, right? It becomes important because imagine you are sending, some reads and writes as a device like a NIC device to memory, which can be in multiple places. They don't have to worry about, oh, did this write get to the other memory device or not? Because you just told them that, hey, you can do them in any order. I'm enforcing my ordering here. So now they get those writes. Each of those memory controllers or memory type 3 devices, there might be, whatever, 10, 15 or whatever in a system. Each of them might get a different write from the same device. They just do it locally. Now, if there is a coherency conflict, let's say if you're writing to a device and let's say the post processor has its say, right? You need to then issue a back invalidate. But most of the time when the IO is accessing the memory, we really do not expect there to be a coherency conflict. It can happen, but it's not a huge probability event. And even if there was a conflict, if you look into going back and forth to the processor, if you count the number of hops back and forth, you will still come out ahead with this back invalidate that we have.
Is it possible to connect with multiple racks with CXL 3.0?
So from a protocol point of view, you can connect multiple racks. I think the real question is the physical reach, right? So, cables can go only as electrical cables can only go a certain distance. So as long as those can be done, yes, you can reach them using electrical. The other option is you can do E to O to E conversion, and of course the distance problems get solved, right? So from a CXL protocol point of view, we wanted to solve the large scale thing from a protocol perspective, and of course there is the reach aspect of it. As I said, within a rack, the reach is easy with cables. Across racks, it's a challenge with electrical cables, but that's where you can deploy optical. Danny, did you want to add something there?
Yeah, maybe I'll add, with the port-based routing, we've implemented fabrics that can reach up to, over 4,000 devices. So, to implement something that large, fundamentally, you would think you'd be able, or you need to go beyond a single rack. As Devendra mentioned, there's obviously some physical limitations with respect to SI and the physical link, but those can be overcome with different mechanisms such as optical.
Or even retimers, you can add those
or retimers.
Longer, yeah.
So in a GFAM scenario, how do we meet the latency and bandwidth? Are any retimers planned? If so, how many are allowed?
So let me do the easier one, right? Are any retimers planned? Yes, we support retimers, right? And that's independent of GFAM or no GFAM, right? So CXL has been supporting retimers. In fact, we have, we even when we were doing the 128B, 130B encoding, we had things like, sync header off for doing low latency in the retimers. So those are supported current, and those are basically, you can pretty much use a PCI retimer and it will still work, right? And there is some CXL optimization. If you get that, you're going to get additional lower latency. Up to 2 retimers in a given link is allowed. Now, in the GFAM scenario, how do we meet the latency and bandwidth requirements? So the bandwidth is easy, right? I mean, it's whatever bandwidth you get. Most likely, it's going to be how many conflict cases you are dealing with. Now, on the question of latency, it becomes interesting because, of course, you are going to go through multiple levels of checks, especially for the shared memory. So you're going to increase the latency a bit. But the most important thing there will be if you run into conflict scenarios. That's where your latency can start going up because you're trying to resolve coherency conflicts there. So that's a little bit of a nuanced answer there. Danny, did you want to add something?
Yeah. So the latency targets that Devendra mentioned earlier in the call are just that, right? They're targets, and those, as we expand to larger and larger fabrics, that it'll be harder to hit some of those targets. But obviously, you get the benefit of the expansion to more devices. So it's not super critical that those targets get hit when you talk about, say, a fully deployed 4,000 device fabric, for example. There's the potential of tiering things, such as like tiering memory. So you may have longer latency to certain memory devices, for example, but that could be acceptable based on your workload and the overall TCO of the system. So there's a lot of trade-offs there when you start talking about latency and fabrics in particular that are going to be system dependent.
So will traditional PCIe devices attached to a CXL 3.0 switch port be able to use the UIO peer-to-peer flows with other PCIe and or CXL devices attached to the switch?
So the UIO part we are developing with PCI 6 so that PCIe devices can also take advantage of that. I'm assuming if it is for other PCI devices, remember that memory is non-coherent memory. So yeah, they can still do UIO to the non-coherent memory, but primarily, that coherent memory is where you are going to get a lot of benefit from a CXL perspective. So you should be able to take advantage of that even for PCIe, assuming PCIe devices have implemented UIO semantics.
Okay. Well, thank you, Debendra and Danny, for sharing your expertise. The presentation slides will be available on CXL Consortium's website, and we will address all the questions we received today in a future blog post. So please follow the CXL Consortium on Twitter and LinkedIn for updates. Danny, back to you.
Okay, thanks, Elza. And thanks everybody for attending and submitting your questions. The presentation recording is going to be available on the CXL Consortium YouTube channel. The slides will be available on the consortium website. We hope you'll reach out with any questions you may have after reviewing the evaluation copy of the 3.0 specification, which can also be found on our website at computeexpresslink.org. And thanks again. Have a wonderful remainder of your week.